Next up, we have Israel Morales, who will be telling us about big mapping class groups from a geometric group theory perspective. So please.
Okay. So, first of all, thanks to the organizers for inviting me to give this talk, especially to you, Menche, for being very attentive all the time. So, I need to give some disclaimers. My presentation is more informative than the present results or research results. So much of what I will say has been covered in previous talks. So my talk will be probably a bit short. Okay, I divided this talk into two parts. In the first part, I will want to talk about mapping class groups or surfaces again, in general. And in particular, I will focus my attention on mapping class group of infinite type surfaces, which are called in the rest literature as big mapping class groups. And this area is new with important developments in the last 5 years, maybe. So people are asking if the perspective given from the framework of geometric group theory is useful to understand the, the algebraic or topological structure of a big mapping class. My intention in the second part is precisely to let you know the latest advances in this direction, mainly from the following the Rosendal work. Finally, I will ask some questions that I consider good to reflect on, precisely because the merger of the big mapping class group and geometric group theory is taking its first steps. Okay. So let me start by telling you a few words about topological surfaces. Topological surfaces are completely classified, especially the classification of orientable and connected surfaces is very nice. Any topological surface of this kind is completely characterized up to homeomorphisms by three invariants. The first is the genus that can be infinite in this case. The space of n's, which is a closed subspace of the Cantor set, and the space of n's accumulated by genus, that it is a closed subspace of the space of n's. Intuitively, the space of n's captures the ways that we can go to infinite in the surface, and the space of n's accumulated by genus, as the name indicates, captures all the ways to go to infinity by genus. So some examples are the following. By the fundamental group of a surface, we can distinguish two kinds of surfaces. We say that a topological surface is of finite type if its fundamental group is finitely generated. Otherwise, we say that the surface is of infinite type. By the classification theorem of surfaces, any finite type surfaces are precisely those that have a finite genus and their n space is finite or empty. In this case, our n's are isolated points and are often called surfaces punctures. So obviously, in this case, as the genus is finite, this finite type surface does not have infinite genus. So the space of n's accumulated by genus is empty in this case. The second example, The second example is the surface of infinite type that is obtained from the sphere. From the sphere by eliminating an infinite set of isolated points that accumulate in a single point. to get a real surface, we also need to remove this single point or the single accumulation point. And to someone familiar with the language of ordinal numbers, we simply say that we remove from the sphere a set homeomorphic to the ordinal number omega plus 1. This surface is homeomorphic to R2 minus the natural numbers on the real line, and it is called the flux surface. The next example is another infinite surface. This surface has infinite genus, only one end, it is accumulated by genus. This surface is called launch net monster. The next one is the Cantor tree surface. It is the infinite type surface obtained from the sphere, deleting a Cantor set on it. So we can see that it has genus 0 and does not have ends accumulated by genus, and his space of ends coincides with the removed Cantor set. And last, finally, we have the blooming Cantor tree surface. That is simply the Cantor tree surface with genus, decorated with genus everywhere. That means we declare that all the ends of the Cantor tree surface are accumulated by genus. Okay, so there are some examples to have in mind. So the next, now we are in position to define the mapping class group of a surface. Here, Homeo plus of S denotes the group of all homeomorphisms of S to itself, which preserve the orientation of the surface. Naturally, this group is a topological group with the compact open topology. And if we denote by Homeo 0 of S, the path connected component of the identity in Homeo plus, then Homeo 0 is a normal closed subgroup of Homeo plus. Hence, the mapping class group of a surface S in general, finite or infinite type, is defined as the quotient of the Homeo plus modulus Homeo 0. As I said, the mapping class group coincides with the set of all connected components of the group, of the topological group Homeo plus of S. Similarly, is defined the extended mapping class group of the surface, but in this case, we include all the orientation reversing homomorphism of the surface. The people familiar with this concept of mapping class group, the interpretation of the elements of the mapping class group is as isotopy classes of homomorphisms that we could have defined it like this. Naturally, we give the quotient topology to the mapping class group, inherit from the quotient mapping, and in general, it doesn't matter if the surface is of finite or infinite type. The mapping class group of a topological surface is a topological group. Okay. So from the middle of the last century until now, we have accumulated a lot of information about mapping class groups of finite type surfaces. In recent literature, this class of groups are called the classical mapping class groups. Some facts that I want to remember about classical mapping class groups is that they are discrete with the topology before in here, and also they are finally generated. Okay, these all results. On the other hand, on the other side, mapping class groups of infinite type surfaces, or big mapping class groups, as the people refers to this class of groups, the topology of big mapping class groups is more interesting. They are uncountable, Hausdorff. They have the structure of Polish group, that is a topological group separable and completely metrizable. They are not locally compact, and they are topologically perfect, and not compactly generated. So the question here is, so to give you the idea how we can obtain that a big mapping class group is a Polish group, is in the following sense. For this, we use the curve graph. The curve graph is a graph associated to a surface. This graph has as vertices the set of all isotopy classes of simple closed groups, and edges are declared as a pair of vertices that does not intersect with this joint representative. So we give to the automorphism group of the curve graph the permutation topology that is generated by translation of stabilizers of finite set of vertices. So now the natural action of the extended mapping class group on the curve graph by simplification automorphisms give us the homomorphism of group C. And moreover, C is, and using words of many people, we see that this homomorphism of groups is an isomorphism of topological groups. So finally, the mapping class group is isomorphic to the automorphism group of a countable graph. So by a theorem of Cameron, the automorphism group of a countable graph is a closed subgroup of the symmetric group, the infinite symmetric group. Therefore, as the property of being Polish is closed undertaking closed subgroups, we obtain that the extended mapping class group is Polish. So that is a very, very detailed proof. So at this point, I finished the first part of the talk. So next, I move on to talk about how people are adapting the geometric group theory perspective to study big mapping class groups. Sorry. Okay. We recall that if we have a group G with a generating set A, then we can define the work metric with respect to the generating set A. So it is a classical result of Bromo that if G is generated by two finite sets, then the corresponding work metrics are quasi-isometry. So this is our theorem, and we know that this was the starting point to relate algebraic properties of the group of the group that is finally generated with Higgs large scale geometry. And more generally, the people are interested in saying what algebraic properties of the group can be derived from Higgs action on geometric objects with good large scale properties. And the example, or the classical example, are mapping class group of an exact surface. So the next step to extend the theory, in their beautiful book, Cornelier and De La Hare extended the theory of geometric group theory to locally compact groups. In this case, to make everything work well, they replace the notion of finite generating sets with compact generating sets and obtain a similar result. So at this point, our groups which we are interested in studying are Polish groups, not locally compact and not compactly generated. So we come to the crucial question, is there a generic notion of generating set for a Polish group? And that makes sense in this case with the perspective of geometric group theory. So Rosendal recently introduced the notion of a coarsely bounded set to overcome this difficulty. So this is the we say that a subset A of a group G is a CV or coarsely bonded set if for any neighborhood of the identity V, there exists a finite set F and there exists a power K such that A is contained in the K product of F with B. So one example of this is, or as example, in locally compact and sigma compact groups, CV sets are precisely the relatively compact sets. But more importantly, in Polish groups, the notion of CV sets have a nice geometric interpretation. A subset of a Polish group G is CV if and only if A orbits of any continuous action of G by isometries on a metric space X are finite. So, oh, sorry. Okay. This result becomes relevant after we know that there are groups of automorphisms that are globally CV, such as the connected component of the identity of the group of the homomorphism of a compact manifold, for example, or the infinite symmetric group. The interpretation here is that it is impossible to study this type of this kind of groups from a large scale perspective because his action in any geometric space, or in this case metric space, has bounded orbits. So by the hand of Rosendal, we know that if a Polish group is generated by two CV sets, then the corresponding world metrics are quasi-isometric. This result is the starting point to study the large-scale geometry of CV-generated big mapping clusters, as we can see. Okay, having said all of the above, the following problem makes sense. Classify all CV-generated big mapping clusters. So Mann and Raffi have made progress in this direction. Time does not permit to give a detailed description of the work and his results. So only I want to mention that there is a big class, a big family of big mapping class groups that are CV generated. Among CV generated big mapping class groups, there are also which are globally CV. And surprisingly, there are big mapping class which are not CV generated. So even with the great work of Mann and Raffi, at the moment there is no complete answer to the problem. Okay. On the other hand, it makes sense to ask about the quasi-isometric invariance of big mapping class groups, at least for those that are CV generated. One problem is to classify CV generated big mapping class groups, which are Gromov hyperbolic. So far, we only know of one big mapping class group that is hyperbolic. Schaffer-Cohen proved that the mapping class group of R2 minus a Cantor set is hyperbolic. But the problem is still largely open. I don't know if there is progress in this direction. The next problem, and in the main of the big problem that in the area of big mapping class group is that is try to relate the large-scale geometry of CV-generated big mapping class group to their algebraic properties. At the moment, nothing is clear in this context. It seems difficult at first glance. So to study so the next thing that I want to do in the future is study the next topic. To study the probability of big mapping class group, we can replace the same question applied to a quasi-isometric countable graph to the group. This is the case of the orbit graph. For this, we use strongly that the big mapping class group is isomorphic to the automorphism group of the curve graph. So let M the curve graph and consider the diagonal action of the mapping class group on the n Cartesian product of M. So take a bar element of Mn and O a family of finite orbits. Okay, so the orbit graph of a surface is with this data we construct the orbit graph of the surface S that is defined as follows. Vertices is the set of coincide with the orbit of a bar. And edges are pairs of vertices which are not equal, okay? And two vertices B and C spans an edge if they are distinct and the orbit of the pair BC or CB is in the collection mode. The result here is that if this graph is quasi-isometric to the big mapping class group when the group is CB generated. So our hope is that we have the hope that this graph may be more useful in addressing the hyperbolicity problem of big mapping class groups. So to prove this theorem, it's very useful to use the Schwarz-Minor lemma, in this case, adapted to the theory of Rosendal. So thanks.
Right, let's thank the speaker. And are there any questions? Since we still have a bit of time, could you say a little bit more about the proof of this last proposition?
Sorry, this proposition.
Yes.
Yes. The idea is that proof that okay. The idea is to prove that the stabilizer of this element, the stabilizer of this element is a neighborhood of the identity. So the idea is to prove that this neighborhood CB generate ECB and generate the orbit mapping class. So in this case, that is the generating set, and we use the standard version of the Schwarz-Minor lemma to prove that this is the mapping class group is quasi-symmetric to the graph.
Okay. Thank you. Any other questions? Well, seeing none, let's thank the speaker again.